Lecture 3.9, Derivatives of Exponential and Logarithmic Functions. And this is Mount Rushmore in South Dakota, place everyone ought to visit at least once. Look at the graph of y equals e to the x. The slope at x equals 0 appears to be 1. If we assume this to be true, then the limit as h goes to 0 of e to the 0 plus h minus e to the 0 over h equals 1. That, of course, is the definition of derivative. Now we attempt to find a general formula for the derivative of y equals e to the x using the definition. The derivative with respect to x of e to the x equals the limit as h goes to 0 of e to the x plus h minus e to the x over h, which is the same as the limit as h goes to 0 of e to the x times e to the h minus e to the x over h. Remember, when we multiply like bases, we add exponents. So going the other way, we can expand this to multiplying like bases. Now we can factor an e to the x out of the numerator, and we have the limit as h goes to 0 of e to the x times e to the h minus 1 over h. But there's no h involved in e to the x, so we can take the e to the x and factor it out of the limit. But this is the slope at x equals 0, which we found in our first step, and which we have assumed to be 1, which leaves us e to the x times 1, or e to the x. So the derivative with respect to x of e to the x is e to the x. E to the x is its own derivative. If we incorporate the chain rule, we get d dx e to the u equals e to the u du dx. We can now use this formula to find the derivative of a to the x. But before we go on, I should just mention that this is pretty much every calculus student's favorite formula, because when we see the derivative of e to the x, it is super easy. It's just e to the x. So if we start with d dx a to the x, because e to the x and ln x are inverse functions, we can write this as d dx e to the ln a to the x. And because we're taking a log, we can move the exponent out in front of the log. And so we have d dx e to the x ln a. Using the chain rule, we have e to the x ln a times the derivative of x ln a. Because ln a is a constant, we get e to the x ln a times ln a. However, we recognize e to the x ln a because we've seen it before right here. We had e to the x ln a. E to the x ln a is the same as a to the x. So we rewrite this as a to the x ln a. Incorporating the chain rule, we get d dx a to the u equals a to the u ln a du dx. So far today we have d dx e to the u equals e to the u du dx, and d dx a to the u equals a to the u ln a du dx. Now it is relatively easy to find the derivative of ln x. Starting with y equals ln x, we exponentiate both sides, getting e to the y equals x, and then take the derivative of both sides, so we have d dx e to the y equals d dx x. But on the left side, we get e to the y dy dx using the chain rule. On the right side, the derivative with respect to x of x is just 1. So solving for dy dx, we have dy dx equals 1 over e to the y. But remember that y is ln x and e to the y is x. So now we have d dx ln x equals 1 over x. Once again, incorporating the chain rule, we get d dx ln u equals 1 over u du dx. To find the derivative of a common log function, you could just use the change of base rule for logs. d dx log x equals d dx ln x over ln 10, or 1 over ln 10 d dx ln x, which becomes 1 over ln 10 times 1 over x. The formula for the derivative of a log of any base other than e is d dx log au equals 1 over u ln a du dx. So here are our formulas.